Good afternoon, KF7IJZ here, back from a long winter's break with the first video of the spring. Now that it is springtime here in the United States, a lot of hams are preparing to head outside, preparing to operate portably. Field day is in about 2 months. And I wanted to take this opportunity to compare two different batteries that have come across my desk here in the last year that I've had an opportunity to use a little bit, get familiar with their capabilities, and I wanted to present the information of the differences between them today. On the left, we have a standard AGM absorbed glass mat sealed lead acid battery. The type of thing you could pick up locally at a Batteries Plus. These range anywhere from $15 online to $35 to $40 locally in a local store like Batteries Plus retail. And on the right, we have an A123 Systems lithium iron phosphate sealed lead acid replacement battery. This battery is available online from buyA123batteries.com, which I'll put a link down here at the bottom. This battery cost quite a bit more at about $125, but I want to take the opportunity to compare the two, and so let's get started. So the very first thing you will notice is that these batteries are more or less the exact same size, the exact same terminal arrangement. The left battery is the AGM battery, the orange top battery is the A123 Systems. These batteries are approximately 6 inches long by approximately just a little over 3.5 inches wide. And then if I pull them up on their ends, they're also about 2.5 inches deep, a little bit more than that. They both use F-type terminals, which this is just a PowerWorks cable I picked up to slide on there to make it easy to use these with Anderson power poles. So physically, they're the exact same size, and of course, given that this battery is meant to be a replacement for applications where one would use this battery, that makes sense. All right, the first thing that we'll start comparing, and what may be truthfully one of the most important things, is the weight. Now, I've stolen my wife's kitchen scale so it would fit on the desk, and down here is where you'll see the figure. I apologize. The lighting of my workbench are these overhead LEDs, and so it's often difficult to get a good angle and still see everything. But let's start with the sealed lead acid battery, and we'll put that on the scale, and we see we get E's, which tells me that the scale is not actually capable of reading the weight of this battery. Now, what I know is I know these batteries tend to weigh between like 4.5 to 5 pounds. So we start off with a battery that weighs approximately 4.5 to 5 pounds. Now if we move on to the A123 battery, we stick that on there, you'll see that this battery comes in at 2 pounds 0.20 ounces. So we'll just call that 2 pounds. So immediately it's apparent that there is a huge weight difference between the two. Weight isn't the only thing that's different about these batteries. Inside the A123 battery, you actually have 8 A123 26650 lithium iron phosphate cells. These cells have a nominal voltage of 3.3 volts each and are rated at 2.3 to 2.4 amp hours each. Inside here, the configuration is 4 in series in order to get you into the 12 volt range, and then 2 of those sets in parallel to give you a 4S2P configuration. Now, of course, lithium iron phosphate batteries require a lot of more delicate overcharging protection, undercharging protection, and then balancing to make sure that all those cells stay approximately the same voltage. There is actually a battery management system built into this. The BMS in this ensures that you don't overcharge the battery, therefore it has an overvoltage protection. It has undervoltage protection because if you run these too low, they're pretty much guaranteed dead. Sometimes with lead acid batteries there's some forgiveness, but if you run lithium batteries too low, they're pretty much kaput. And then it also is capable of doing overcurrent protection. In fact, if you look here, there's actually a fuse holder. And if I can get this open, there's a standard 30 amp A123, or not, I'm sorry, a standard 30 amp ATC fuse in here. So the other thing the battery management system does is that it allows you to not have to use a special charger dedicated to charging lithium iron phosphate batteries, and allows you to also plug this into any standard system that would normally charge an AGM battery. For instance, I charge this routinely with a battery tender. I have put this before on solar charge controllers meant for lead acid. And it does quite well because the battery management system converts the voltages coming in from those chargers into what is needed by this pack. One other major difference that I will talk about between these two batteries before we get into the deep dive on the actual electrical characteristics is the number of discharge cycles these batteries are rated at. Generally speaking, fully discharging AGM batteries to 10.5 volts or even worse below generally will significantly reduce the life cycle of these. In fact, normally you will see a number of charge and discharge cycles rated anywhere from 500 to 800 on these, and that's normally rated at about an 80% depth of discharge. And at 80% depth of discharge, you're at about 11.5 or 11.6 volts, if I remember correctly. Same thing here is that depth of discharge is generally rated in terms of 80% depth of discharge, but on these you will routinely see ratings of 2,000 discharge cycles on the lithium cells, which basically, in one manner of thinking, that this battery will last 3 to 4 times as long from a number of discharges cycles as this one will, given the same application. And speaking of electrical characteristics, if we pause for a moment, we see that this battery is rated at 12 volts, 9 amp hours, 0.36 watts per cell, so 15 minutes. And of course, this battery actually came out of a brand new APC UPS. One of the two batteries in their 24 volt pack was dead. This is the one that was good. So I salvaged it for radio purposes. So, I mean, they rate these in terms of time because the UPS this came out of, is rated for approximately 15 minutes with 2 of these in it. But, yeah, so you see 9 amp hours. And what's interesting about this size battery in general, if I pull back, you will often see batteries this size rated everywhere from, I've seen them as low as 7 amp hours, and I've actually seen some people try to claim you could get 11 amp hours out of this out of this battery. Now remember, lead acid batteries generally are rated at what is called the 20-hour rate. And what that means is in order to get 9 amp hours, the battery was discharged at, or for 20 hours from full charge down to 10.5 volts. The rate of discharge, so what was the current being applied to the battery, can be found by dividing the amp hour rating by 20 hours. In this case, just to make the math easy, you'll see that it's about 1/10 of an amp would be the discharge rate. So if we come over to the A123 battery, there's the model number, again 12 volt DC equivalent, 60 watt hours or 4.6 amp hours. Now right off the bat, that number is approximately half of the 9 that we saw on the other battery. And I'm going to be honest with you, I have not found I've not found any information anywhere that explains how this basically how these rates are determined. I've had a conversation with one large-scale lithium iron phosphate battery manufacturer who explains that their rates are generally calculated at 0.5 C. So in the case of a 4.6 amp hour battery, they would discharge this at a rate of 2.3 amps in order to come up with that number, which obviously is significantly higher than the lead acid battery. So the sad thing is as a consumer, you immediately think that, okay, twice the weight for the lead acid battery, twice the power, maybe it's worth it. But this is one of the areas where things like the amp hour ratings are misleading. And what we're going to actually do is I have battery testers where I can hook each one of these up to constant current or constant power loads and drain them down to a usable voltage or a preset voltage, and we can actually see how much energy is in the battery. One other thing that I will point out, if you have watched my video about batteries and solar, we have to remember that for amateur purposes, our radios really stop being happy at around just under 11.8 volts. I have now personally set my cutoff voltage for applications involving radio at 12 volts. So at 12 volts, you've actually only taken this battery down 50%. So what's interesting about this is already, even if this 9 amp hour number were accurate, if I can really only take one of these AGM batteries down to 50%, I'm already going from 9 amp hours down to 4.5, which puts us back into the rating here. Because one of the other things too, ignoring all the battery management stuff in here, is that these cells, they have a nominal voltage of 3.3. You can run these cells down to into the 2s, but the system won't allow it to do it. But they will end up lasting to a lower voltage safely than you'll have here. At the end of the day, though, that doesn't really matter, because we will set the test up to cut off at 12 volts, and that's what we will use as our basis of comparison. So over the winter break, one of the things that I was able to do is take the opportunity to upgrade some of the equipment on my bench. And what I've done, in addition to adding a current limiting high power supply, switching power supply, which I use when testing solar charge controllers, I've added a new DC electronic load. Previously, I've used the West Mountain Radio Computerized Battery Analyzer 4, which is an absolutely wonderful instrument. USB, can do up to 150 watts. But in order to go up from there, you have to buy one of their amplifiers at about $800–900, and that takes you to 500 watts. But I wanted to go somewhere kind of in between. So this is a device called the Menuo M9712, and this load will do, this is a DC load that will handle 0 to 150 volts and a total of 300 watts, which means I can do twice the current that I can do with the West Mountain Radio unit. This is manufactured and comes from Japan. The story behind this is the designer of this company used to be an engineer for BK Precision, I've heard. Basically took some of these designs, made a couple of improvements, and started selling them his own. This was about, I want to say around $600 on Amazon, and then another like $50 to get that little white box, which is the USB interface, so you can connect it to a computer. A couple of interesting things about this, and I should probably do a separate video sometime, but this load can do constant current, constant voltage, constant power, and constant resistance. It has terminals for remote sensing, so you can sense the voltage at the battery versus through the load. It has some other neat things too. It can do duty cycle testing. It's programmable. A lot of the software gets a lot of data out of it. It's really pretty cool. But for our purposes, we will be doing the battery test, where I will start off by setting an end test voltage of, in this case, 12 volts. And then I will come back and I can set a current. And I'm going to do several iterations. Before we get testing, I will add that the conditions of test is that each one of these batteries will be charged to the green status with the battery tender, left to sit there for about an hour. And then testing will generally begin immediately after, or as it comes off the charger. So I have just taken our lead acid battery off the charger and connected it to the load. We're stable at about 13.2 volts. And we're going to start off this first battery test at 1/4 of an amp. So I come down. So as the test begins, you can see immediately the battery voltage drops off, and 3.245 watts. And then you see the actual current that it's been being pulled at. And then here's our running count of amp hours. Now, the total test time ran for 16 hours 47 minutes. And next we start with the A123 Systems battery, which coming right off the battery tender, and total as well as the total running time. And now we will start the AGM battery off again at the 1 amp test. One of the really nice features of the Menuo DC load is in the battery testing module here, I'm able to specify a customized list of discharging currents and delays. For the purposes of this test, I'm going to simulate a 50% duty cycle of transmitting and receiving. This test will load the battery at 3 amps for 10 seconds and then load it at a quarter amp for 10 seconds and then just repeat that until we've hit 12 volts. We're now going to press the start button on the computer and you'll see we're loaded at 3 amps. And then you see we drop to a quarter amp. And then we're going to shoot back up to 3 amps. And it'll keep doing this until the voltage gets down to 12 volts. And now that we've concluded our test, we take a moment to actually look at our data. Here I've made a quick table. In the 4 columns across the top, the 2 on the left in gray are the results for the AGM batteries, the total time running under the discharge rate, and the total amp hours measured for the discharge rate. And in the 2 green columns on the right, we have the total time run for the lithium iron phosphate batteries, as well as the total amp hours measured for the lithium iron phosphate batteries. And as we see it at a quarter amp, the times are actually fairly similar. And again, this would simulate receive only. But we got a total of 16 hours 47 minutes out of the AGM battery and 18 hours 52 minutes, so almost a difference of 2 hours. Rated amp hours pretty close, 4.18 for AGM, 4.71 for the lithium iron phosphate. At 1 amp hour, though, the story of the difference between lithium iron phosphate and AGM really starts to come into focus. At the 1 amp rate, which would simulate running like an FT 857 or 897 or an ICOM 7000 on receive only, we only get 3 hours and 34 minutes out of the AGM battery, 4 hours and 43 minutes, so over an hour better on that. And of course you see the total amp hours start to decrease for the AGM battery at the higher draw, and that's because the Pukert effect is more pronounced in AGM batteries. The higher the current, the lower overall total energy available out of the battery. On the lithium iron phosphate side, we see that there's actually very little difference, 4.7 amp hours total, a difference of 0.01 amp hours at 4 times the discharge rate. And then finally, for our modeled usage of oscillating between a quarter amp and 3 amps, simulating calling CQ continuously for 10 seconds and listening for 10 seconds, we get a total of 1 hour 38 minutes operation on an AGM battery, but 2 hours and 52 minutes operation on the lithium iron phosphate. In this particular instance, we have almost twice the operating capacity with a lithium iron phosphate battery. The Pukert effect again is seen because we see that we drop from 3.56 amp hours down to 2.65, and you see very little change with the lithium iron phosphate. So from a performance perspective, ignoring all other factors, the data really draws out that the lithium iron phosphate battery is the clear winner for this intended use. Now, before we move on to the next part of the analysis, which is the cost part of the analysis, I wanted to throw this table up real quickly, again, to remind us of the overall performance and cost factors we're looking at. The AGM battery can be had anywhere from $15 to $40 for a 7-ish amp hour pack. I've chosen the middle for 25 because I think that's what you would pay locally at a Batteries Plus to pick one of these up. And there are batteries in this price range on eBay and Amazon, and again, there are cheaper options, but I'm trying to pick something in the middle. On the lithium iron phosphate front, the battery is definitely $125. I've not seen them cheaper anywhere, so 5 times the cost. Now, the total cycle life of AGM chemistry is often quoted as 500 to 800 cycles. Now, this factor is supposed to be determined and bounded by what's your depth of discharge when doing the test. Granted, in both of our cases, we're only running the batteries down to 12 volts, which for an AGM battery is still, well, I think that's, if I remember correctly, 60% of discharge, 50% of discharge, somewhere in that range. So technically, we're probably not getting to the area where we're really worried about killing the total number of discharge cycles, but to make the math easy, I'm going with what I see are common published specs, which are 500 to 800 for AGM, and we're going to use the median of 650 total cycles. On the lithium iron phosphate side, We routinely see published specs of 1,000 to 2,000 total cycles. Again, we're not dropping it down to the bottom voltage. In fact, we're not really getting anywhere close to it, stopping at 12 volts. So we're using the median value of 1,500 cycles. What I'm going to do is compare the total cost of an amp hour when measured over the entire cycle life of the battery to see how they compare from a cost perspective. So what I'm doing is taking the 650 or the 1,500 approximate median number of cycles. I am multiplying that by the measured amp hour rating for each current draw, and that's giving me a lifetime number of amp hours out of the battery estimated. I'm then taking the cost of the battery and dividing that over the total number of amp hours out of the battery to basically get an estimated cost dollar per amp hour figure, if you will. And finally, we're going to look at the cost factors here in following the formula that I just spoke about. The numbers here, unfortunately, didn't quite tell the story I was hoping for, and I think part of this is the relatively high retail price of my lithium iron phosphate from A123. Again, these numbers get even worse if you look at the fact that you could, in theory, pick up a $15 AGM 7 amp hour cell. But regardless, using the factors that I presented previously, at a quarter amp, the AGM battery is definitely the better value. If you are going to factor in cost, because an amp hour only costs you about a cent. It's actually a little bit less than that, but I rounded everything to the nearest cent in this table. At 1 amp, again, the AGM is still the better value per amp hour over the lifetime. Again, these numbers are over the lifetime of the batteries. But at 1 amp, it's 11 cents per amp hour, and using the 10 seconds of a quarter amp, 10 seconds of 3 amps, that goes up to 15 cents per amp hour. On the LiFePo side, we stay continuously flat at 18 cents per amp hour, pretty much over the life of the battery. And if I had done maybe a 5 amp test, at that point we may have seen the AGM battery actually cross over where the cost per amp hour may have increased to the point that in a high current situation, the lithium iron phosphate battery really is the better choice. So overall, from a performance and operating perspective, purely looking at short-term in the field one-off performance, the lithium iron phosphate battery is definitely the clear winner as far as giving you more operating time, not sagging under heavy loads, etc. Certainly being much lighter. But in the cost perspective, at least in the short run for QRP operator type numbers, it looks like the AGM battery may still be a better value, strictly looking at cost per amp hour of operation under the factors that I presented in the previous slide. Overall, I think you have to take into account other factors. Again, if you combine, especially at that quarter amp, 3 amp model, which is pretty consistent with what a field operator is going to do, the lighter weight lithium iron phosphate battery mixed with the longer operating time may be enough to actually close that 3 cent per amp hour gap. But either way, you're going to pick what's right for you. Some folks, it's easier for them to make a short outlay of cash every so often to get those lead acid batteries versus investing in the bigger one. I'm just presenting the information that I found in my testing. So as per usual, thank you very much for sticking with it to this point. I know it's been quite a long video. I hope you've enjoyed it. Please let me know in the comments below if you get value out of this and want to see additional testing. I'm always trying to get my hands on different batteries and whatnot, and now that I have a much better lab setup, it's easier for me to do this kind of testing. So thank you very much again for watching, and until next time, this is KF7IJZ.